If you read writings from many of the old astronomers from 100 and 200 and 300 years ago, especially if they were charting the data by hand, you'll see that they were always amazed at looking at the heavens. They talk about the music of the spheres. They talk about the cosmic dance. And I want to try and share just a little bit of that with you. This is a simulation from a website called PHET, P-H-E-T, called My Solar System. And so here is a star and a large planet. And if we start the orbital precession going, first of all, you'll notice, although we tend to ignore it, both objects are tugging on each other because forces come in. You can see the sun has a bit of a wobble. Now, that's not the Earth causing it. The Earth causes the sun to wobble much smaller than that. But it is very, very noticeable. What I want to show you is the sun, the Earth, and the moon. So the moon goes around the Earth while the Earth goes around the sun. I want you to try and imagine what path the moon traces out as the Earth moves around the sun. And I'm about to make you smile. So try and imagine it. It looks like this. And you can start to imagine astronomers when they were charting this, when they were graphing this by hand, when they were slowly, carefully matching the data. You can imagine partway through a smile of delight and joy would start to cross their face as they realized, although from our viewpoint the moon moves in a circle, if you were hovered above the solar system looking down, that's what it traces out. This is the music of the spheres, the cosmic dance that they like to talk about. It's gorgeous. It's really cool. And not what any of you were imagining, I don't think. It doesn't form a circle at all. It does to us, but not as far as the sun is concerned. You can have a sun, a planet, and a comet. So here is a planet, here is a comet. All comets orbit the sun, but their orbits aren't necessarily stable. So if you watch the blue planet, not only is the sun tugging on it, if you watch the blue comet, not only is the sun tugging on it, it was deflected by the planet as it went by, which knocked it off of its orbital pattern slightly. Most comets do end up in the sun. A binary star. Luke Skywalker grew up on Tatooine, which had two suns. It's perfectly feasible to mathematically model two stars and a planet orbiting with them. The only issue is you'd get some very interesting situations. For example, right there, sorry, keep going, I'm too slow. Right here, where is nighttime? Not really anywhere, especially if I go right to there, when the planet was right there, there is no night. It's getting hit from both sides. So it would be interesting if life did evolve on such a planet, what kind of nocturnal, diurnal rhythms they would have and things like that. But it's perfectly, you can model it mathematically. Of course, you have to be a bit careful. You have to get the model just right. If things change ever so slightly, you might end up with something that is nowhere near as stable. Will this be stable? It might be. I'll show you another one. You could have four stars orbiting each other. I don't know if we've found this before, but you can model it mathematically. The reason I'm not sure if we've found this before is if you're even slightly unstable, if you're even slightly not lined up correctly, you very quickly end up with a chaotic system and things don't quite work out. You don't get that lovely four-star ballet. So it would have to just work out really nice. But you can certainly model it. One of the things that we do when we send probes to outer space, because it all comes down to weight, mass is the key thing. Mass does not cancel out when you're looking at how much fuel you need. What we try and do is we do what's called a slingshot maneuver. A slingshot maneuver is when we send our probe close to another planet, so that planet pulls it in with its gravity, giving it a speed boost, and we slingshot it around. So here is the probe, here is the planet, and if I start, if you watch, we're going to get a slingshot right there. This thing picked up some kinetic energy from the planet. We can even do a double slingshot. So here is our probe. There's one and there's two slingshots. We've done more than that. I'll show you what I think might be the prettiest orbital path I've ever seen in a little bit. So what does the moon look like as it orbits the Earth? Gorgeous. Really cool. Example 6, pick your notes. I like example 6, I like example 6, I like example 6. Example 6 is a nice question. Last day I said to you that there were 3 variables: orbital radius, orbital period, and orbital speed. And I said if I give you any one, you can find the other 2. Lena, I lied. There's 4 variables. Orbital period, orbital speed, orbital radius, or altitude, because if I give you the altitude above the planet, you just add the radius of the planet, and now you have orbital radius. So they're kind of part and parcel the same thing. A satellite has an orbital altitude of 1.26 meters above the Earth. What's its orbital radius? I would mentally or actually underline the word orbit. That's my trigger. When I see the word orbit, what do I write? I don't write a circle. I write something is something. Gravity, big G, big M, little m over r squared, is what's pulling me in a circle. In fact, you know what? Ooh. Wait a minute. Do I need to do that for part A? I don't need to do, you can scribble that out. Part A, it just wants, and they gave me altitude. Don't give me any altitude, but they gave me altitude. And we said, hey, its altitude is the orbital radius minus the radius of the Earth. How would I find the orbital radius if I know the altitude and I know the planet? Okay, so let's do that first. Let's read the question carefully. Our orb is going to be altitude plus our planet. So it's going to be 1.26 times 10 to the 6th, so 1.2 times 10 to the 6th plus 6.38 times 10 to the 6th. Do I have the same exponent in my scientific notation? You can do this in your head. It's going to be 1.2 plus 6.38. I think it's going to be 7.58 times 10 to the 6th. And you can also try this on your calculator, but I think you will get 7.58 times 10 to the 6th. So that's going to be our orbital radius. Now, B. What do they want me to find? Orbital. Now, gravity is what's pulling me. And look up. Since they said speed or velocity, if it's okay with you, I'm going to go straight to saying v squared over r. Yes? What cancels here in this version? Yep. Does the r always cancel? It depends on how we're starting. In fact, I've seen this equation before. Orbital speed is going to be the square root of big G, big M over r, and that r is the orbital radius. 6.67 times 10 to the negative 11. 5.98 times 10 to the 24th. 7.58 times 10 to the 6th. .67 times 10 to the negative 11. 5.98 times 10 to the 24th divided by 7.58 times 10 to the 6th. Any typos? Doesn't look like it. Square root answer button. And we did say orbital speeds tend to be in the thousands. I think if we were right on the surface of the Earth, it was like just under 8,000. We're not very high, so it should be a little less than 8,000. We got a little less than... I'm good with this. I think we did one also where we were 20,000 kilometers up, and that ended up being, I think, in the 3,900 or something. It gives you an idea how they kind of fit together. So 7,250 meters per second. What's C want me to find? Now, I could find the period. Look up, don't write this down, look up. I could go V equals 2 pi r over the period. I could. Do I know V? Just found it. Do I know R? Yeah. And I probably will for this question because I've done A and B, because I know the orbital speed and I know the orbital radius. That'll work. Or I could go gravity is what's pulling me in a circle, and here we ended up with T equaling the square root of 4 pi squared r cubed over big G, big M. So if you want to, you can write both of those down, I guess. Which one would be cleaner to use? How would I get the T by itself? And by the way, why can I use this? Because what path am I tracing out? So why don't I use circular speed? Especially since I just found it and it's stored on my calculator. I guess T is going to be 2 pi r over V. T is going to be 2 pi 7.58 times 10 to the 6th all over. I'll write 7250, but it's stored on my calculator. I'll use the more accurate one. 2 pi r over answer button. You get 6566. I'll go 6570. Is that right? You try it? Just to confirm that both methods work, I'll do this one really quickly. 4 pi squared r 7.58 times 10 to the 6th cubed divided by bracket big G big M no typos, Mr. Dewick. Looks good. Square root of that. Bang on, even to about 12 sig figs. So, I don't care which one you use. I'll be honest, it's such a habit for me to write gravity is what's pulling me in a circle that I may do that and not even notice that if I'm in a rush. I got to be paying attention and spot that. Okay. What's your homework? Number 1. Number 2. So in number 2, you're going to find Mercury's orbital speed. I gave you Mercury's orbital radius. You have the mass of the sun on your sheet. I think the mass of Mercury should cancel, so you don't need it. Number 3, you are above the moon. So please use mass of the moon and radiuses of the moon. 4 is good. 5 is good. 6 is good. 7 is good. Skip 8. 9 is good. 10 is pretty tricky. I'll see if you can pull it off. Skip 11. 12 is good. 13 is good. 14 is good. 15 is good. I skipped 8 and 11. Put your pencils down and look up.